So what will be the source for today? I have a survey article on grossing groups. I don't like to recommend my own work, but since this is actually in part about my own theorems, I might as well give this. So it's called Grossing Groups. Ideas and Perspectives. So this is a source. Most of what I will be talking about today will be in there. You may still want to take notes, simply because I give a shorter version here, but it is completely up to you. Wait a second. It's the problem when you... Yeah, so if people never had lunch, things would go quicker, wouldn't they be? All right, very well. So we have studied so far the case of a commutative ring, as I say. So in particular Z, we have studied when is it the case that A plus A is less than a constant times A for A in the integers. So the same techniques work for A in G abelian. And more generally, they also work, the situation is not too different for G nilpotent. Nilpotent is something more general than abelian. Can you read this well? I think there's something odd with the chalk. Very well. So where did we have lunch? I cannot remember. At any rate, it does not matter. So what do I mean by nilpotent? Well, something that you can see as a paradigmatic example is set of matrices which are upper triangular with ones on the diagonal. X, Y, Z in R are abelian. All right. At any rate, these are groups that are almost abelian. So you can ask yourself, what happens in the general case when G is not abelian and nowhere close to abelian? So what about G non-abelian? Well, just a tiny change in notation. We will write times instead of plus, simply because in a non-commutative group, you generally write times instead of plus. So geometric group theory, G infinite So we study G infinite. G is infinite, and we study A to the K as K goes to infinity. So that's what Gromov and all of his friends do. Then there's subgroup classification. We study A such that well, of course, this is a bit of a joke. What does it mean that we study A such that this is the case? Well, if A contains A and A squared equals A, this implies that A is a subgroup of G. So, of course, when you study subgroup classification, you're classifying subgroups. which is the same, as I have just said, as to study the sets that don't grow at all, the sets with k equals to 1. Well, is this a joke? Not really, because it turns out that many of the techniques used in subgroup classification turn out to be robust, or at least some are. So they give you the properties of subgroups, that is, of sets A such that A squared is no larger than A. But some of these techniques also tell you something about the case in which A squared is barely larger than A. That is this case. And again about notation, let me make sure.
What about a symmetric? A should be symmetric?
It doesn't much matter, but we can impose a condition if we want to. Let me explain. Sorry, yes, that's a good question.
Not that A is not a subgroup of J, but a subgroup of J.
I think that in here, if you put the identities in A, this is guaranteed to be true. I think.
It's A is a finite. No, J.
A is finite. G can be infinite, but A is always finite.
A is finite. That's okay.
All right. Well, at any rate, so we want to study something that is not quite the same question as either of them. So it's really, when is A times A not much larger? So, which is not quite the same question as the first one. Okay. Well, I left some space here. Why did I leave some space here? It's because it actually makes sense to study AAA here. Why is that? It's because in an abelian group, if you show that A plus itself 100 times is small, or if you show that A plus itself 100 times is large, that implies that the A plus A is large by Plunica-Ruja. So let me state it as follows. In abelian groups, you have that A plus A, if A plus A is small, this implies that A plus itself L times is small. Right? That's what we showed. And so the first half of this, remember that we had that A plus A is small, already implied that, and was the easy half. The harder half was a part of the argument due to Petridis. Well, that second half is actually does not work over non-abelian groups. Only the first half does. So in non-abelian groups, so remember, we have multiplicative notation. So this implies AL, KLA. In fact, it also implies, just to emphasize it, though it's also true for abelian groups, that if you take the inverses, and this answers your question about whether we assume A to be symmetric, this means that yes, it makes sense to assume that it is symmetric. It doesn't change the question much. AOLA. So this is still Ruja, in a sense. I mean, he did not state it for non-abelian groups, but the same proof works. But the last step would not work. So this does not imply, with any constant, that A times itself 3 times is smaller than k to power times a. So here I could give you some examples, but I think you are just as good as finding them. So let's take some subgroup H of some group G, such that there is some conjugate of H whose intersection with H is just not the identity. Then what can you do? You can take A is equal to H union little h, and this satisfies, well, what does it satisfy? A squared, well, what is A squared? You tell me. A squared would be little h squared. It would also be big H squared, which is just big H. It would also be little h times big H and big H times little h. So it would be of size at minus 3a. But A cubed contains, you see, A cubed contains h, little h, h. And it's not hard to show that this is of size of h squared. You cannot have any repetitions because of this condition. So this. Ta-da. All right. So let me see. All right. So this just tells us that we should not expect to show that A plus A or A times A is always much larger than A. Sometimes it isn't. And moreover, the right thing to prove is that A times A is large. And also, if we show that A times itself 100 times is large, this shows that A times A is large. So that's why the question is raised this way. Very well. So what shall we focus on, though? So we have this question. We can focus on simple groups, simply because everything, just like matter is made out of atoms, groups are made out of simple groups. What are simple groups? They are groups without normal subgroups other than themselves and the identity. So it's just like prime numbers are to natural numbers. So there are groups such that the only normal subgroups are the identity and H equals G. So, in fact, we know, and this is a very, well, I don't know whether to call it a very deep theorem or a theorem with an extremely long proof with many deep ideas, but well, we have a list of all finite simple groups. Of course, let me specify non-abelian, because then mod pz is simple without being is simple and abelian, but we are focusing on the non-abelian case. Now, the finite simple non-abelian groups can be put into three buckets. One of the buckets contains beautiful and interesting monsters. In fact, one of them is called the monster, but there's only a finite number of them, so we don't care. So we just put them under the carpet. I say almost simple because I will simplify things a little. Here you have the matrix groups, and here you have the permutation groups. Let me say the symmetric group. Yes. So what are these? Matrix groups are just things such as SLN over a finite field. So SLN, the special linear group, is just a group of n by n matrices with entries in FQ and determinant 1.
Okay, can you
and here,
explain what is almost simple?
Almost simple would mean that, well, I mean that either it has, like the symmetric group, a subgroup of bounded index, in this case index 2, that is simple, or something that has a quotient by, you know, a set of two elements.
Subgroup of factor group.
Yeah, a very big subgroup which is simple, or a very big quotient which is simple. If you want to know almost, I would write P here and everybody would be happy, and here I would write alternating instead of symmetric.
Okay, I know, but the question is why you write SLN but not GLN?
Oh, because GLN would not be almost, or rather, GLN has SLN as something of finite, of course, these are all finite, but unbounded index. In GLN, SLN is something of index of size Q, roughly, Q minus 1.
Yes.
Yes, Q is unbounded. Q is not a finite amount of fudge.
Okay,
I did all of the, I was saying this just to simplify matters, no pun intended, but apparently did not. Really, we work with SLN, but it's not really simple. In order to make it simple, you put a P in front, and then you put plus minus 1. And now everybody is very happy, and I don't have to put almost here.
No, I think if n is bigger than 2, that
PSLN is simple.
Yes, of course, but it's not factor only plus minus 1, no?
It is plus minus. Yes, it is. Or roots of okay, roots of unity you mean, but it's something that is bounded by, for n fixed, it's something of bounded index.
Yes. It's index depend on Q?
No, it does not depend on Q. It depends on
no,
it depends only on n. It's bounded independently of Q.
Okay, it's because it's a Q divided by 2. For example, if S.
Yeah, but it's bounded independently of Q.
Okay, it's of course, okay.
Well, all of the point of this conversation is that our consciences are clean. Okay, thank you. Yes. So this meta group would be Cman, the group of permutations of n elements. Yes. At any rate, you can in practice work with Cman or with SLN. These are all I'm saying is that all the interesting cases, in essence, reduce to working on Cman or working on SLN or SON, one of the classical groups, in essence. Very well. So what about them? You have the classical groups. So you know some of the other ones. And you have the symmetric group. That's essentially it. Then you have a finite number of monsters, but since we're looking for asymptotic statements, we don't care that much about the finite number of groups. It's like saying, well, you know, children should not worry because there's only a finite number of monsters under their beds. Very well, so here's something I proved. So let G be SL2FP. So this is just, you know, SL2FP is just a group of all matrices A, B, C, D. It's a special case of that in FP and with the determinant 1. Everybody happy, I hope. And just to make sure, so by brackets I mean the group generated Is group generation clear? So it's just a, the group generated by A is just a set of, is the group of all products, all finite products of elements of A and its inverses. Very well. So you have a subset A of G, A in G, and you're also happy with this, right? A to the K all along has been, do I need to write it down? So it's all the products of A things. Very well. All right, so the point is, so you have a set of generators A of G, then either A will grow by a lot, not by a constant, but by a power here, or well, let me put the original statement. The only way that this will not grow a lot is if you hit the entire group. Obviously, this cannot be true if A is already G or almost G, but that's essentially, that's the only exception. So either you have a lot of growth, or this times itself a constant number of times is G. So K absolute. So some notes. In 2, we now know that this is true with K equals 3. Or even just that A, this is an improvement due to Nikolov, Piver, and Gowers. One, as I was saying before, 3 is a magic number here, in that it is enough to show that this with the inverses 100 times is greater than A to, say, 1 plus 1 over 200, say, since this implies 1. By Ruja. Very well. Since then, so today and tomorrow, today and not next Monday even, but the Monday after the conference, will be devoted in part to a proof of this. I will not give you quite the first proof I gave. I will give you a more modern proof, if you wish, that incorporates some ideas from other people as well, because this newer proof is more easily generalizable to other groups, and this has been generalized many times. So just to give you a minimum of history, since then, this has been generalized to well, so just to give you an idea, so I will put horizontally certain generalizations. Why? This was done 2 times by 2 students, Deny and Varju, a postdoc. And there's also a generalization to SQ2 by Burgan-Gambord. And let me emphasize that their generalization here is a difficult generalization. In the sense that actually the same proof that gives you this gives you the same result with a finite for G equal to SL2 over an infinite group, say SL2C. The same proof works, so you just delete a few pages. You don't need anything about subgroup structure. Now, for what happens is that very often when you want some consequences over C, what you want from here is not quite this statement, but a somewhat harder one. Something concerning measures. I will talk more about that in the following class, which will be the last one. So here, this result framed on sets implies, as we will later see, a result on measures. You can phrase this in terms of measures. But over an infinite group, the result on measures is harder. And they actually prove the result on measures. Because there's a predecessor, by the way, for SL2R, I believe, Elekes-Király. I did not know this at the time. So Elekes and Király have a statement which is more or less equivalent to this for finite sets over SL2R. But it's nice, but the methods don't work here. And it's these methods that generalize. Because over R, say, if all you're looking for is results about sets, then you can use the fact that R is an ordered field. You have a certain topology that works very nicely to separate things. And
there really is not a proof about algebraic group, yes? It's not a proof about algebraic group, yes? You cannot see on SL2 as an algebraic group, yes?
Yeah, it is about an algebraic group.
If you prove this theorem for as an algebraic group, it does not matter, is it?
No, yeah, that's the point. If you prove it for SL2FP, then if you're careful and you do some modifications, then you're going to be able to prove it for SL2 over other fields. The problem is that over SL2R, if you prove it for SL2R, that doesn't necessarily mean that you have proven it.
Yes,
precisely, because SL2R has a lot more structure, it has a topology. By the way, this is something that, well, all of this is just talk, I'm not putting it on the board, but in general, no, maybe I should put it on the board. So, I don't want to be unfair, but life is easier over R. So say results such as H. So there were results of this kind. And these originally played a role there. So-called sum product theorems were known for A in R before, as in a generation before A in FP. This is so-called sum product theorem. This was proven by Erdős and Szemerédi around 1970, but this was proven only about 12 years ago over FP by Burgan-Katstau. Just a bit of philosophy. So is this, again, we have had a small conversation, but I have tried to extract the moral from it. Is the moral clear? At any rate, so in all of this, there's an issue though. Why have I put it here horizontally? It's because these groups look different. SU2 certainly looks different, but if you look at the Lie algebra, it's just the same. So in some sense, these are natural generalizations of that.
Okay, you said about generalizations. Can one prove this for any simple group?
Yeah, wait. This is what I'm going to draw. So it took me, I mean, this is a completely subjective statement, but it took me a lot of work to generalize this to SL3. And here in the paper, I called it SL3, but half of the paper is about general linear groups. It's just that I couldn't manage to finish the proof myself. There were there was other work. Let me mention also. So this was part of the main trunk. Then my postdoc and I tried. Well, some people generously have said that we proved half of the case of FLN. So this is my postdoc, Nick Gill. But we got sort of stuck. We couldn't do SON. But other people generalized the proof to SON. We were a bit stuck with SLN. We proved what we thought was the harder half of the proof, but we could not do SON, curiously. But since then, this has been done. So now this is known for SLN and, in fact, well, let me put the names first. So this was done simultaneously by two groups of people, Piver and Szabo and Brouillard-Grintao. So, and any any simple group of Lie type. Let me put in quotation marks because I will not give the formal definition. But this covers pretty much every simple matrix group. So SLN, PSLN, SON, P, no, just put P wherever you wish, SP to N and so on, but also the twisted groups and whatnot.
Oh, it's a twisted group. And
twisted groups, everything.
And for yes678, no, for exceptional Lie group.
Yes, that too. That, you know, P-Saba, I think it's really filled all the corners. Yes.
And for
no, but not for the symmetric group. That's something that remained. And here there's something that P-Saba would like to emphasize. That there's one remaining weakness, in that in all of these, the key thing here is that delta was an absolute constant, does not depend on P, otherwise the statement would be empty. But here, yes.
Is it delta an absolute constant?
That's a problem. So delta depends on the rank, which for i.e. depends on n. And it must depend in the sense that the result would be false for an absolute constant delta in SLN. There are examples by Piber and by other people that show that in SLN, in such a result, delta has to depend on n. It's not a very nasty dependence. The counterexamples show that the dependence has to be at least linear, and I think Piber and Sabo got cubic dependence. So it's okay, but still there's a weakness there, and it's closely related to the fact that the last group to resist, and still partly resisting, is Simen. In Simen, the result will be false as stated. So, but can one modify the result so that it will be true in Simen? Actually, one can. Well, let me give you, yes, but it's not, so I have been able, I will talk about consequences of this result next time, in particular the consequences on small diameter. So myself and Sheresh managed to show that the diameter of Simen is always small. But we haven't got a full classification of all A that violate that. So I will speak about small diameter, but just to give you an idea of why this is important. So what is the diameter? It's the least k for which A to the k is entire group G. And this gives you immediately that the diameter of SL2 with respect to any set of generators A is small. And we can prove the same sort of conclusion, though somewhat weaker, as a somewhat weaker conclusion for Simen, that was Helfgott-Sheresh. But today let us stick to not so much to the consequences as to the methods, and we will give most of the proof today. So let us say, blah, 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 blah. All right, so as I was saying, I will give you a proof that is not quite the same as the first proof I gave. It will be something that generalizes more easily, and things have also become a bit more conceptual over time. So, what are some ideas? We would study different actions homomorphisms. What do I mean by the automorphisms of X? If X is a set, this is just a symmetric group on X, all permutations of X. If X is a linear space, then of course it means linear automorphisms and so on. All right, so the notion of action, как action по-русски? Действие. Just as in real life. Действие. Very good. So this is just a действие. Действие. Действие? Действие. Very good. So this is a действие. And the notation is known to all. You don't like the notation?
Yes, I do.
You prefer to curl it?
Analytic people say this is not a good notation. It's okay.
Even with a curl, they don't like it? You prefer D?
Yes.
I never do that. But why do you want that?
Because the simple
Arrow is a function.
arrow is a function, yes.
Yes, but if I curl it a little, it's okay, maybe. So this is also okay, right?
No, it's embedded.
No, but embedded has the
Embedded
same level
upper.
of the arrow and the it's not an embedded.
No.
At least it's not all written embedded.
Okay.
All right. If I don't put this, remind me. Very well. So this is one thing. So some notation. There's so-called orbits and stabilizers. Now, the stabilizer of a point is just the set of all G that leave it fixed. So it's a subgroup of G. And people are fine with less than to mean subgroup. Okay. Now orbits, they are generally defined in terms of a subgroup, but you can define them for any set. And AX is of course just the things to which A takes X. Okay. So what else? Another thing is that sets that grow slowly, as I was saying before, behave much like groups in certain circumstances. Or even statements about sets in general can be modified, about groups in general, can be modified to hold for sets in general. Let me explain what I mean. So sets that grow slowly. In this case, it could be A less than KA, or AAA, meaning A cubed, less than A to the 1 plus delta, behave like subgroups. And some statements on subgroups can be generalized to all groups, or to all sets. In what sense? What could that ever mean? Well, let me give you an example, which does turn out to be a key tool. So there's something that gets the grandiloquent name of theorem, even though it's just a little lemma, but it's a very important little lemma. It gets called a theorem, at least in English, because that's what undergrads see in their first group theory course. It's one of 3 theorems that they see. So it's the orbit stabilizer theorem. Как это по-русски? Тривиальная лемма, может быть? Let me say it. So let G be a group. G fancy. How do you do this in LaTeX, by the way? An action. Does anybody know the LaTeX command?
I think yes.
So H is a subgroup. Ah, very well. Then the intersection of H, which is stabilizer of X, well, you know, assuming that these guys are finite for the most part, this is going to be the size of H divided by the size of the orbit. So the stabilizer in a subgroup is the size of the group divided by the size of the orbit. And the proof here, well, the proof here is sort of trivial. Actually, yes, let me just write, pretty trivial. Well, can anybody do it? No, как это по-русски? Без имени. Это как остров без имени в Санкт-Петербурге.
Теорема об орбитах и стабилизаторах, не знаю.
Да, это теорема также по-русски.
Да, об орбитах и стабилизаторах.
Я думал, что это слишком маленький для быть теорема по-русски.
Ну и не знаю, ну как, что...
At any rate, can anybody see how to prove this? You have seen this before, and well, you know how to prove this. So basically, you just multiply by hx on both sides, and you get an injection. Yeah, but it's a very trivial but important remark in order to show that the size of a set is smaller than the size of another set. It's enough to construct an injection, though. But in fact, that's how you prove this. Well, it turns out that surprisingly, well, I mean, at first sight, this statement actually holds not just for subgroups H, but for subsets A, if you modify it a little. So let G act on a set X. A is a subset of G, little x. Then I will not write A, I will write A times A inverse, stabilizer of X, at least AX, and is at most A squared AX. So proof number one is by pigeonhole, and number two is pretty trivial. So just try to do it and you will get this result. So notice that the orbit stabilizer theorem is a special case of this. Because if you assume that A is a subgroup, then A inverse, A, and A squared, they are all just H. So it's H everywhere. And of course you have two inequalities, but one of them is that the left side is at most the right side, and the other one is that the left side is at least the right side. So they give you this equality. So this is, strictly speaking, really a more general version of this. But you see how it's really true for any set A. You have, in general, here we have not even assumed that A grows slowly. We have just replaced some instances of H by A, and others by A times A, others by A inverse A, and so on. And this is not the only statement that can be generalized in this fashion. Let me give you an application to convince you that this is not trivial. So let G act on G by conjugation. Because, well, it also acts by left and right translation, but those actions are really boring. So G sends H to H inverse. Very well. Then what are the orbits? the orbit of H under G, say, what would that be? What would be the orbit of H under conjugation? The conjugacy class of H, exactly. The orbit of H under a set would be GH G inverse G in A, which is a subset of AH A inverse intersection the conjugacy class of G. The stabilizer of H, what is the stabilizer of H? Under the conjugacy action. So you have a set H, so it's H sits in G, which is X in this case. So yes, it's the centralizer. Yes. Как centralizer по-русски? Centralizator. So it's a subgroup of all things that commute with H. Very well, so we get as a corollary of the theorem for sets is that for any A in G and H in A to the L, A inverse, the intersection of A inverse with the centralizer of H is of size at least A divided by A to the L plus 2 intersection conjugacy class of H. Very well. So now that the basic concepts are here, I will start with the main ideas of the proof. In fact, I will try to give a complete proof. All right. As we will see, we will really get much closer to the final result once we are able to construct elements of A of a special form. For instance, that is why it was important to show as a consequence of orbit stabilizer that you could give a lower bound for the number of elements of A inverse A that lie in a centralizer. A centralizer is something very special. If you show that there are elements other than the identity of A or A squared in the centralizer, you have got somewhere. But first of all, we would like to get at least some assurance that there are elements of A not of a special form. So how do we know that our elements are not all, say, upper triangular, or, well, that's easy, it's because they generate the group. But how do we know that they are not all of trace 2, say, or so on? For instance, we need elements with two distinct eigenvalues. It's what's called regular semi-simple in this context. So you could say, well, this is very easy because almost all elements of G have two distinct eigenvalues. It's a generic condition. But how do you guarantee that? I mean, maybe your set A consists only of elements without distinct eigenvalues. Well, that might happen, and they might still generate G somehow. But what we are going to see is that then, at least in A squared or A cubed, we are guaranteed elements with two distinct eigenvalues. You don't need to do this case by case. You can do it. You can do it in full generality. In general, what do I mean by a special shape? We mean satisfying an equation or one of a finite set of equations. So for any equation that the entries of the matrix might satisfy, we are guaranteed that there is at least one element, in fact many elements, of a or a squared or a to a bounded power that do not satisfy that equation. So so this is true for most, in fact almost all H in G, but we need it for some H in L. So ABCD has distinct, so let me unpack this a little. So this has distinct eigenvalues when the trace is not plus minus 2. So to speak in full generality, so we need A and D not to satisfy an equation. To speak in the language of algebraic geometry, we need elements of A to the L that lie outside a variety of positive codimension. The language is familiar to everybody, or I will explain it a little. H is not in W, and what is W? W is the union of two irreducible of positive codimension. In fact, codimension 1, as it happens. W1 is just the things that are. So variety многообразие, алгебраически многообразие. So you have these two irreducible guys, and W is just this reducible многообразие, but all its components have positive codimension, and so you can imagine a hypersurface in space, and you need elements, not just of G. We know that almost everything in space lies outside a surface, a given surface. But we actually need elements of our set A, or A to a constant power, that lie outside that surface.
Now, why this variety is irreducible?
These two? Well, they are. Doesn't much matter. But in fact, W isn't. That's why I wrote it as 2. What matters is, I wanted to say a variety of positive codimension, but one can speak of only of the codimension of an irreducible variety. That's why I wrote it as a union of irreducible varieties, and I said, I should say, we are interested in elements that lie outside a variety, all of whose irreducible components have positive codimension. This corner of the room is happy. What about the rest of the room? Why is the rest of the room so happy all the time? Well, so what would be the So this particular case, you could do it by hand. In fact, when I was first working on these things, I was proving this sort of thing by hand. It's not too difficult to show that if you have a set of generators of SL2FP, then you can indeed have an element of say A cubed that has trace not equal to 2 or minus 2. It's something very concrete. But then you ask yourself, well, can I give a general argument? And the answer is yes. So this is what people call escape. It is not particularly new. I mean, people were doing this over C, and the same proof works over FP. You could say it's classical, but let G be a group. G acts on some sort of finite dimensional vector space. WV is a subvariety. Every reducible component of V has what I mentioned. These are just our usual assumptions. You have a set A. We can assume without any harm that the identity is there and A is equal to its own inverse. And X in V is such that AX, the orbit, is not contained completely in V. There's at least one point in the orbit outside W. Then the conclusion is, oh, then at least one element of ALX lies outside W. L depends only on W, in fact only on the degree and the dimension. Of course, the dimension of W I actually mean the dimension of its irreducible components, blah, blah, blah. Very well, and ditto for the degree. So just to give you a picture of what I'm talking about. So let V say, you know, k squared, or affine space, if you prefer this notation. And let W be a curve here, say, and say I have a point here, and G is acting on this curve in such a way that, well, many elements of the orbit might lie here, but there's at least one element that so this is X, and there's at least one element of the orbit. It might be 8 to 100 million times X. There's at least one element of the orbit that lies outside the curve. And what this proposition is telling you is that if we know this, then in fact you know that, say, a squared times x does not lie within the curve. That there is, just because you eventually get out of the curve, you can get out of the curve in very few steps. A number of steps that depends only on the degree and the dimension of the curve. Sounds fishy, doesn't it? But it's true. So let me prove a special case, but in fact the proof for the special case will work in general. I will tell you at the end a couple of things that make it work in general. The special case will just be that of W linear and irreducible. So instead of a curve, think of a line or a space. Why would that be true then? That if you eventually get out of the subspace, then you get out of the subspace in very few steps. Can assume that, of course, that X lies on. Otherwise, it's obvious, it's trivial. You are already out of the thing. So we will proceed by induction. Base case. The base case will be dimension 0. And then, because things are irreducible, the W is a single point. And then the statement is clear. Why is the statement clear? Not you, somebody else? Извините?
Нет, там на втором шагу видно.
На первом. Discuss about this.
Yes. What about it?
Okay. What if we have an x?
Yes.
Is it? Is it a p? Is it a constant or?
What p? There's no p.
In a px and
Where?
It's L. Okay. Is L is a constant L?
L, yes. L depends only on the degree and the dimension of on degree and dimension. Depends on nothing else. It does not depend on x or on what have you, or even on the group. It depends only on the dimension and degree of W and V. Yes.
Depends on K.
No, what K? No, it doesn't depend on K. Haha, it's hard to believe. That's good. You know, the statement is non-trivial. All right, so let us proceed. Where did I leave my notes? Well, okay, you can prove this for dimensions. So why is this true?
Because equals 1.
Yes, exactly. If you get out, so if you did not get out of the point right away, that would mean that Ax equals x, and then you never get out of the point. So you're done. Notice that for the case of not irreducible things, it's also true. It's just a little bit less trivial. You have a finite set of points, and you know that you're going to play hopscotch only for as many steps as there are points in the set. Hopscotch, Paruski? Probitskaya?
Jump.
Jump, no. Это не важно, но. Да.
Классики.
Классики? But right now we have the simplifying as. So that's what happens in dimension. Yes. So classic, it's when the dimension is 0 and W is not irreducible. Yeah. But here we are dealing with an irreducible case. So. What a strange name for a game. At any rate, so assume, now it is the inductive step. So assume that the statement is true for all W prime with dimension of W prime smaller than dimension of W. And so contradiction. You see what I'm doing? Yes. So first of all, I'm stating I'm claiming that GW cannot equal W, because if GW equal W, then, well, X lies on W by assumption, but this is equal to GL inverse, blah, 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 W. It's the same thing. W is invariant under the set generated by A. But this would mean that any element of the group generated by A times X lies on W. But this is not what we were assuming. So GW is not equal to W for some G in A. But what does that mean? That means that you have W here and you have GW somewhere else. So intersection will be of lower dimension than W. The advantage of W being irreducible. It's an irreducible variety. This is pretty much the only place in which it's convenient for things to be linear and irreducible. Sorry.
But can it be 0?
Can the intersection be 0? Sure. So much the better, then we are done. But all right, it's an irreducible variety or empty of this dimension, lower dimension of knowledge. By the inductive hypothesis,
it's an algebraic variety, yes? W is an algebraic variety.
Yes, it's an algebraic variety.
Yes.
Yes.
Okay.
That's why it's not some sort of, it's not a topological, I mean, what sense would it mean to be topological? Yeah, in FP the only varieties are algebraic varieties.
Yes, of course.
Yes, all right. Whenever I said variety today, I meant algebraic variety. In English, variety means variety. Topological varieties are called manifolds.
Yeah. This theorem for FP is trivial because you have a finite number of points.
No, it's not trivial because all the constants should be independent of P.
Yeah.
It's an entire key point. You cannot allow yourself a single dependency on P or your final theorem becomes trivial.
Yes, of course. But if L depends on
the degree, but that's fine.
What
on the dimension?
It's degree.
The degree of, I mean, the number of irreducible components, the degree of each of them, the dimension of each of them.
Yes.
Very well. All right, so by the inductive hypothesis there are some elements of a L prime, or there is some element of blah blah blah, such that G prime X does not lie on the smaller variety, just because the theorem has already been proven for lower dimension. Then either, of course, this means that either G prime X does not lie on W, or G prime X does not lie on GW, that is, or G inverse G prime X does not lie on W. So one of these two. But then we're done, just with L equal to L prime. L prime plus 1. So we just need one more step to get out of the thing. So this is true. Well, of course we have, this is the easy case when there's just one irreducible component of degree 1. But what do we do in general? Simply because we said that the intersection is an irreducible variety. Whereas usually when you have the intersection of two varieties that are not of degree 1, then the intersection is several irreducible varieties. But that's no big deal. That's what I'm about to say right now. So in fact, so without linearity, we use Bézout. What does Bézout say? So it says that the degree of two things, say u and v, is at most the degree of u times v, for some notion of degree. What we really need is that some sort of bound on the degree. Again, I have not defined quite what degree is. It's a bit hairy when you deal with non-irreducible varieties, but it works.
Yes,
So
of course it works, but it's a difficult theorem on the positive characteristic.
I know.
But it's true, of course.
Generalize, Bézout.
Yes.
Happy?
Yes.
Yeah, actually, whom is it really due to? Because the version I usually use was it was formalized by Fulton and McPherson, but it was known long before. So it is from what, the time of Vail and company?
Oh, yeah, I don't know. And at the positive characteristic, I don't know.
Yeah, so that's why I imagine that the positive characteristic must be from the 40s or 50s.
Yes.
Or a bit maybe 30s, but not before. So we need a bound in terms of that's all we need really, because the only way where we use linearity was for this. So we need some sort of control on the number of irreducible varieties under degree, which is what degree means. You can think of the degree of a non-irreducible variety as being somehow if you wish, the total of the product. Say that the total of all the degree of the sum of all the degrees of the irreducible components. Fair enough. At any rate, so that's about doing it without linearity. Of course, if you don't assume linearity, you have some control on the degree, but you also want to be able to deal with non-irreducible things, because intersection of two irreducible varieties of degree greater than 1 will be non-irreducible. So what about the case of non-irreducible? Well, in fact, the idea is the same. The induction just gets more complicated. I will leave it as an exercise. The induction is, yes, on the maximum degree of the components of W and the number of components of maximum degree. The point is that when you have something non-irreducible and you take the intersection of GW with W, some of the time the degree of the maximum degree of the components of W might go down, and that's good. But if that doesn't happen, at least you can guarantee that the number of components of maximum dimension will have gone down. And so the induction finishes. Yeah, as you said, we have not used linearity in any heavy way. The proof basically works in general. All right. So what about what I call dimensional estimates? So this is the idea of escape, well, the general statement of escape, and this is the idea of the proof. So this shows us, and we can use the same proof to show not just that there exists a G like this, but that a positive proportion of all G's are like that. You can prove that at least a constant times cardinality of A, elements of A to the L, obey this, unsurprisingly. All right, so it shows that there are always elements that are not very special, and that in fact you can prove you can find quite a lot of them. So, what about more general statements? Can one give a better bound for how many elements there are of a special form? Well, at least on simple groups you can. This is not use anything about the group G. It is only now that we will be using something about the group G. Namely that we're working with simple Lie groups, well, groups of Lie type. So, in fact, the first time that I had to give a dimensional estimate was when I had to, and this shows what I mean by a dimensional estimate, that's when I had to show that not too many elements of my set A lie on a torus, that is, lie on are diagonal matrices. It was harder and more important later to show that many do lie there, but first I had to show that not too many lie there. In fact, by the structure of the proof has taken since then, one no longer needs exactly the previous statement, that is to show that there are not too many elements on the torus. But it's still nice to start that way, because it's just like the linear case, say here, it gives you an idea of the essence of the proof. Very well. So dimensional estimates. So let, in general, give me an algebraic group. W is some sort of variety, because an algebraic group works both as a group and as a variety. Very well. So A sits in GK and generates GK, say. Then we want not just to show that there are elements of, say, A to the L outside W, we actually want some sort of good upper bound on AK intersection W. Typically, what we will be aiming for, and we will actually be able to get for simple groups, would be a bound of the following kind. AKL, say, L, is some sort of constant, to the dimension of W divided by the dimension of G. In retrospect, morally, this is how many elements ought to be on A. What is surprising is that you can actually show that. This is how many elements deserve to be on a variety of dimension W. And you can actually show that when G of K is simple. So let me first show you a result, as I was saying, that we no longer use as such, but was the first for me, personally. A field, A subset. By G of K, I just mean SL2 of Fp, or SL2 of K, say. I'm just being very formal here, but nothing is happening here, with A inverse equal to A, E in A. And T is a maximal torus. Is everybody happy with maximal torus or not? Very well, so this is a maximal torus. Well, in K. And if you conjugate it, it's still a maximal torus. So maximal torus is just the group of diagonal matrices under some basis. So that's why I conjugated by G. G is arbitrary. In general, a maximal torus is, well, blah, 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 but in SLN, it's just a group of diagonal matrices under some basis.
the group of diagonal.
Yes. Yes, it's a group of diagonal matrices, and I can.
In a cell, of course, yes.
Yes. Yes. Very well. Then what is a conclusion? Then A intersection T of K will be at most A to the K to the 1/3, where K is an absolute constant. And this is also an absolute constant. Very well. How am I going to show this? So let me give you not possibly the simplest proof, but one that generalizes. And here, 1/3 is nothing magical. It's just the dimension of the torus divided by the dimension of the group. 1 divided by 3. The dimension of SL2 is 3. No, it's 3 variables. Well, 4 variables, but 1 condition. So it's dimension 3. Okay, proof. It's enough to construct an injective map phi such that phi of such that when the arguments lie in A, not just in T of K, then the image lies in AK. Since then, we would have T of K intersection A cubed is the size of the domain, this guy, which is equal to the size of the range, simply because this is an injection, and which is less than the size of A to the K. So you would indeed have the T over K intersection A is at most A to the K to the 1/3. Well, in here, this can be relaxed. It's enough that phi minus 1, that every pre-image doesn't have to be of cardinality 1. It's enough that it will be of bounded size. And this will still be true. If it's bounded to 1, if it sends at most a bounded number of points to a single point, then this still works out, because then the domain is yes, and the domain is bounded by the range. The domain is bounded by, yes, the domain will be bounded by the range times something bounded. You know, if your map phi can take at most 3 points to a single point, then this would still be true. We just need a division by 3 here. No, a multiplication by 3 here. So this is fine. And in fact, you can relax this even more. Or even, you could even say that only, you know, you could have an exceptional set. Outside of which the pre-image is always bounded, or so on, or so on. So you can relax this. So we do not necessarily have to construct an injective map. We can construct something that is like an injective map. All right, so what will phi be? T01, T1. This will be T0, G1, T. Where we will specify in some way for some G1, G2 in A K prime, K prime an absolute constant. Now I will use the most tricky words in the language, easy to show, that there are G1 prime, G2 prime, G of K prime, G, and this is the algebraic completion, such that V, the conjugate of V by G1 prime, and the conjugate G2 prime are linearly independent. V very well, easy to show. In fact, for SL2 it is easy to show. You can show it with your hands. But this is just the one bit in the proof that does not generalize in a trivial way. And I will tell you later how, for other varieties. And I will tell you later how you would do it for general varieties. Yes?
Okay.
Yes. That would have been easier than kneeing, right? But the problem is that I cannot move this up.
Why? I think you can.
No, I cannot. Oh, I see. Wait a second. This is a solution to everything. I see. All right.
Can you explain? You multiply with 3 torus?
Yes, and my hope is to show that this multiplication, if not quite injective, is almost injective for well chosen for some G1, G2 in A to high power.
You go to a book about linear algebra.
Yeah, I'm going down to the Lie algebra. Yeah, so I claim that I can find some elements, at least in the group, for which these guys will be linearly independent. At least at the level of the linear algebra. So at the level, certainly, if you want your map to be injective, so you have these 3 tori. Look at them as circles in 3-dimensional space, and if you want their product to be more or less injective, you certainly want them to go through the origin in different directions, in 3 different directions. So this will be linear independent. So I claim, and for SL2 you can show this with your just computing things, that there are some elements of the group, at least, not necessarily of A, but of the group, such that these 3 guys are linearly independent.
Okay.
Very good. But then what can you do? Well, the pairs for which these folds are a variety. Why are they a variety? Or a subvariety of G. Why? Because not being linearly independent means that a certain determinant is 0. So that's certainly a variety. And what we have just done by, saying that it's easy to show that such elements not on that variety exist, what we have done is show that that's a proper subvariety. If you have a variety and you actually construct an element outside it, that means it's a proper subvariety, obviously. That's what it means. But since this is irreducible, shown this is a proper subvariety. This is not all of G. This is not all of G times C, and so of positive codimension. That's very good. Why is it very good? Well, as soon as you have something that is of positive codimension, you can escape from it. applied with A cross A, which generates G instead of G, and G cross G instead of well, really G cross G supposed to be V cross V instead of V, where G lies in V, which would be affine 4 space. So by escape from varieties, you can actually escape from this variety of positive codimension. There is a pair G1 prime, G2 prime in AL cross AL, where L is a nosworth constant, just a constant whose degree does not depend on the field. There is a pair such that indeed that is satisfied V. These are all of positive codimension. Let me just remove these primes because I don't really need them. But what happens when they are linearly independent? Well, if you just look briefly at this, if you just take the derivative of this map at the origin, you will realize that for these three vectors to be linearly independent means that the derivative of this map is non-singular at the origin. Well, that's a good beginning, right? Because we want to show that this map is almost injective. It's a good beginning to show that there is at least one point, namely the origin, at which the derivative is non-singular. And now how do we continue? Well, again, space of TTT at which d phi is degenerate, meaning singular. Degenerate sounds so judgmental and old-fashioned. The points at which the derivative is non-singular, or the points at which it is singular, form a variety of positive codimension. Well, they form a variety, that's clear. So the points at which the derivative is singular are the points at which the determinant of the derivative vanishes. Hence, those points form a variety. We have just shown, by constructing a point at which it's non-singular, we have just shown that it's a variety of positive codimension. We have shown these are properties of a variety, but again, because T is irreducible, and so it has to be of positive codimension. And then what do we have? Do we have escape? Not quite. It's actually a simpler argument. So how do we proceed now? We just need to show that it's enough for this quantitative argument to work for us to have this. Namely, it's enough that phi be non-singular outside, that phi have non-singular derivative outside a variety of positive codimension. Why is that the case? Very well. So we can construct. So there exists W0. There exists a W1 of bounded degree, bounded independently of G1 and G2, of positive codimension, such that for all T0, T1 in T of k cross T of k, not in W1, there are at most O of 1 elements, T2 of Tk, such that T0, T1, T2 lies in W0. That much is clear. It's a very, very simple statement. I'm just saying that outside some very special points, you're going to have that only for a bounded number of T2s, T0, T1, T2 is going to lie on the variety. I'm just taking fibers. And, you know, and there exists W0 of degree 0, 1 such that for all T0 lying in Tk, not in the W0, there exists at most of one elements T1 such that this is exceptional. I'm just breaking down my variety by dimension. No, this is W2. This 1 W2. All right. And now I'm almost at the end of the argument, because here I'm just breaking down this variety. So what now? Given any, I claim that phi inverse y, well, phi restricted to t, t, t outside W0, it's pretty much under that, is bounded. Why? Why is this true? Well, the preimage of a point is going to be a variety. Now suppose that if that variety, and the degree of that variety is bounded by the degree of the map in some way. Now if that variety has got only components of dimension 0, then we're fine. A variety of dimension 0 and bounded degree has a bounded number of points lying on it. So all we have to show is that this preimage does not contain subvarieties of positive dimension. Well, suppose that it did contain varieties of positive dimension, then just pick any point on one of them. Then the derivative at that point cannot be non-singular, it has to be singular. Why? Because here, remember, we're working outside exception W0, so that's going to give us a contradiction. But why is that the case? Because if this contained an irreducible component of dimension greater than 0, the derivative there, well, at any point of the component, would be singular. Yeah. You see, you have this map phi. This map phi is a map from one thing to another thing, and the two things have the same dimension. So if you had a subvariety here that all maps of positive dimension that maps to one point, then the derivative at any point of that variety would have to be singular. But we already constructed this so that at every point of this, the derivative is non-singular, so you would get a contradiction. Что?
Мне кажется, что это просто теорема неявной функции, да? Ну, только здесь у нас производная необычная, да.
I'm using some sort of trivial theorem, but I don't know what its standard name would be. It's not just. I'm just saying it's. Phi is not necessarily linear, but.
Нет, я про то говорю, что это такая как бы вот.
обратные функции не будут алгебраические, да, чтобы
you have to think of the same dimension. So if you had a pre-image that contained a line, then the derivative would have to be singular here, but it's not. We just said that it's not.
I understand the reasoning, yes, but the philosophy is that this is something like inverse function theorem, yes, but we do not have it.
If you wish, I mean, it's yet again, all we can work with is dimensions and the Zariski topology and so on. Yes, because we don't have anything less coarse than that, or not.
If it was on R, not finite fields, yes, it will be a usual analysis, yes?
Yes, you can probably get something qualitatively stronger, and that's essentially what Bourgain and Gambor do in the generalization that I talked about before. That if the derivative is bounded away from zero, you know, it doesn't squeeze things so much. Is that a semi-answer to your semi-question?
Ну, вопрос был просто несодержательный, что с точки зрения это вот, наверное, явный.
Да.
Если вы хотите, да.
Да, но формально вы...
Да. Yes, it's a very weak sort of implicit functions here. If your derivative is not zero, you are not squeezing and you are not losing dimensions. Very well, but then you're almost done. Because that's all that we wanted was to know. Okay, so this is all that we needed. Because it shows very well. That's what we needed. So, in the same way, so there are, of course, this is zero-dimensional, so at most of 1 point. It's not even the same way. There are at most of 1 point on W. There are also at most so here I'm just saying that outside exceptional points the pre-image is bounded, and here I'm saying just that there are very few exceptional points simply because of dimensional arguments. Very well. So we get that the set of x in x, x in the set of what am I doing here? Okay, we've got what we wanted. It's just a matter of language now. I wrote this myself, but I have this little x that shouldn't be here. We've got the point that we wanted because we have shown that the number of things that lie outside W0 of k, but that lie on t here, well, it's really A union, A intersection tk times itself 3 times. This is A intersection t of k minus about the number of exceptions. So say this is a constant c, and so we have got that A over t of k cubed is at most a constant. Well, here's the entire right side. Is at most a constant times A. And so, since it's a constant, we just take roots and we get this at most A to the K to the 1/3. Very well, which is what we wanted. All right. So again, the philosophy is quite simple. We just construct an almost injective map. Here I was just doing a calculation to show that it was almost injective enough. So all we need for the map to be almost injective to get us a quantitatively desirable result is for it to have non-singular derivative almost everywhere, which reduces to showing that it has non-singular derivative somewhere.
Really, you could write this inequality. Really, you solve some linear or not linear system of equation. Really.
Yes, so there are, I mean, all that I needed to show is that there's at least one solution to the system of equations, yes. Oh, yes, so the only thing that I hid under the rug was this little bit, which I already erased, where I said it was easy to show that something was true. Now, if you try to show a completely general statement, and I will write it on the board, that's everything else in the proof just goes through smoothly. That's the only bit that requires extra work. But in fact, as other people did, you can prove that you can solve the linear system of equation just using the fact that you're working with a simple linear group. So let me go quickly over this. In negative time, so general statement. It's that if you have G simple linear group of Lie type, simple group of Lie type, so group of, well, whatever, and you have V as a variety. Oh, let me just call it V. Then the intersection of A with V is at most A to the K. So K will be of 1 depending on the degree of V. Dimension of V for some definition of degree and dimension. And here's dimension of V, dimension of G. This was got in two slightly different ways by P-Sabo. P-Sabo were basically generalizing my arguments. They got something slightly weaker, but for all groups, so even for really, really exotic groups. And Briere-Green-Tao, they were, well, they knew my work, and they were, in their case, it also comes in part from Larsen-Pink. Larsen-Pink had shown this, but not for a set, they have shown it for a subgroup. So this is a less trivial analog of the same thing that happens for the orbit stabilizer theorem. This was known for subgroups, and it turns out to be true for sets. Now, as I said, the easy to show part. Well, let's start to do it just for two vectors. You want to find two linear independent vectors. Say that, and here's where you use simplicity. You have V, want to show there exists a G such that V and G are linearly independent. But then this is just what it means for you to have a simple Lie algebra. There are no ideals in a simple Lie algebra. And the Lie algebra of a simple linear group is simple. But then, of course, you also want 3 independent vectors. But the idea again is the same. You have already constructed 2 independent vectors. This vector space is not invariant under conjugation, so you are going to be able to find something out of it. So, also find G prime such that G prime V, G prime inverse is not in the space generated by V, which you can do, because this is not a simple thing, and so on and so on. Actually, this is what it reduces to. The induction gets a little bit hairier, but the proof works in general. Of course, the dimension of V might not divide the dimension of G, but this will still be true. You will just be you will not be constructing injective maps. You will be constructing maps whose such that the pre-image is not of dimension 0, rather is the pre-image is of dimension no larger than something, and something of smaller dimension. So you will be able to use induction.
Can you describe why for SL2?
Yes.
You cannot describe a simple map from there times there times there. Yes. Really, what is it? Really, it's a map from 2 variables to matrix group, really, yes?
Yes, well, 3 variables, yes.
Yes, no, for 3...
3 copies of the torus to, yes, so you just want to find G1 and G2 such that T goes T0, T1, T2 goes to T0, conjugate of T1, conjugate of T2, so that it's almost injective, that's all you need.
Yes, why you cannot simply describe this? Yes, I don't know. Just, no. Why you need a torus? Why you need complex? I think this is 2 to 4. I don't know.
Oh, but that would be showing absolutely nothing. You could define such a map, but that doesn't show anything.
Why?
Because what you want to show, I mean, what do you get from this? Nothing. You want to show that some map phi, it's not enough for the map phi to be almost injective. You want the map phi, yes, you want it to be almost injective, but you also want this to be contained in a to the k. So you want the A intersection T here and A to the k here, because you want to bound this in terms of that. This bounds nothing in terms of...
how you prove this?
Well, precisely because the map was of the form. This is why we had a map of this form. So this is what I was saying at the end. So this is, I mean, all of these are elements of A to some small power. So this is clearly, so the set of all these things, where it's T0, T1, T2, blah, blah, blah. So the set of all of these things clearly lies in A to the k, some small k. Simply because all of these are elements to A to a small power. So that's on the one end. And these elements lie in A intersection T of k, by definition. So that's why. Whereas this map here doesn't show anything at all. Other questions? Well, all right. So today we did escape, and then using escape, we proved the stronger statement. I mean, once we have the statement of such generality, we no longer need escape, right? We know that not only that there exists element of A to the k outside V, but we know there are plenty of them, because we have bounded how many elements of A to the... You could put L here and KL here. You have bounded how many elements lie inside V. Very well. But we used escape to prove this. Well, next time we will see how to use these dimensional estimates to give a proof, at least for SL2, but a proof that generalizes fairly easily for other groups. You look unhappy.
I don't understand this. No.
This statement or that?
This.
What's the part that's not understandable? So you have this map, but the map was defined so that the image would be where you want it in a to the k. You agree that it does lie in a to the k?
Okay, why?
Because it's a product of things that all lie in A. It's a product of a finite number of things that lie in A. All the T's lie in A, intersection T of K, and all the G1s and G2s also lie in A to the 3 or A to the 4. So that's why we granted all the entire game. First we showed that there exist G's, little g's in big G, for which this is true. Then we said, well, this shows that this is a generic condition that is valid outside a variety of positive codimension. Hence, there must be G1, G2 in A by escape, which satisfy the generic condition. And so we can pick G1, G2 in A.
And K, and how we do that GA and G2 in line A and K?
In A, because of what we said. We first showed they existed, and but by definition, the G's for which that is true, the G's for which the variety, for which the derivative is non-singular, those are G's that lie outside a variety of positive, a variety. The variety, since it's a property variety, by the existence of these things, must be of positive codimension. Hence, by escape, you can find elements of A to a power outside it. So it's the magic of escape. It's enough to show that good things exist, and then good things lie in your A to the L.